Hey everyone, and welcome back to The Explainer. Today, we're taking a really fascinating journey. We're going to start deep in the weeds with a highly specific hardware engineering decision, and we're going to follow it all the way up to a profound design philosophy that honestly, you can apply to just about any project you're working on. We're looking at a system where a single, seemingly restrictive design choice actually ended up unlocking some truly incredible new capabilities. Okay, let's dive right into this. Here is our roadmap for today. We'll start with a quick overview of the PTSG core. Then, we'll ask if its design was a compromise or a foundation. After that, we'll walk through two major doors this design opened, breaking Fmax limits and achieving ultimate multi-sync. Finally, we'll wrap up by looking at how a liability becomes a source of capability. So, Section 1, setting the stage. Let's look at the core technology we're dealing with today. We're talking about the PTSG, which stands for Programmable Timing Sequence Generator. Now, this is a specialized hardware core built specifically for FPGAs, or Field Programmable Gate Arrays. And unlike a general-purpose CPU that kind of juggles a bit of everything, this core has one single vital mission: precise, deterministic timing signal generation and control. It's built for strict, real-time hardware execution, where literally every single fraction of a microsecond matters. What's really cool is how the PTSG perfectly blends software programmability with strict hardware real-time capabilities. It uses a prescaler for deterministic timing control, meaning it divides a reference clock to guarantee absolutely exact timing. It can execute sub-operations entirely in the background without ever disrupting your main timing loops. And it hooks up directly with external logic on the FPGA. And get this, fascinatingly, its entire design process is AI verifiable. The creator actually maintained reasoning trees with AI models like Claude and Gemini and saved their architectural discussions right into the project repository as evidence. It's just a brilliant, next-generation approach to hardware design. Which brings us to Section 2, and a really interesting crossroads. Was this core's design a compromise or a foundation? Because at first, it was perceived as a bit of a liability. In the early stages of building this architecture, the creator made a very specific decision about the free-running prescaler, the internal counter that keeps the time. They decided to make it truly free-running, meaning it's reset only by the global hardware reset when the system actually powers on. It is never realigned, and the local software program is absolutely forbidden from touching it. Now, initially, the creator actually felt kind of apologetic about this. They viewed this free-running counter as a compromise, a liability that just had to be managed, tolerated, and worked around simply because it couldn't be neatly reset by the local code. And this brilliantly illustrates a huge paradigm shift. The old mindset was totally rooted in phase-sensitive design, where you're constantly apologizing for phase shifts, always trying to manage and tolerate these tiny timing differences. But then came the flip, the new mindset of structural phase lock. The creator realized that if they just fully, completely accepted the free-running clock, the hierarchy of the system would naturally keep itself in register. The exact phase of the tick generated by the clock suddenly didn't matter anymore. It wasn't a compromise to manage, it was a rock-solid foundation to build on. Moving into Section 3. Once that mindset shifted, it opened some major doors. Door number 1, breaking the Fmax limits. Let's walk logically through the hardware causality here, because it's pretty elegant. Step 1, you fully accept the free-running clock. Because the system's exact phase no longer matters, we arrive at Step 2. You are now free to register the comparator's output. You see, in hardware, a prescaler is just a counter, and it generates a tick by comparing that counter to a specific target. Usually, that comparison process creates a long, heavy logic delay, a combinational path, which ultimately slows down your maximum clock speed, or your Fmax. But Step 3, by placing a register, a flip-flop, right after that comparator, you basically chop that delay path in half, which leads perfectly to Step 4, achieving a much, much higher clock ceiling. To put that into perspective, by clocking the tick just once before anyone downstream actually uses it, the heavy, slow combinational logic work hits a wall at the flip-flop. What travels onward from there is a pristine, already settled signal. In a traditional phase-sensitive world, inserting this flip-flop would cause a one-clock delay, which would be totally unacceptable. But here, under structural phase lock, it costs absolutely nothing. Because they accepted the free-running clock, this massive architectural optimization for speed was just handed to them as a totally free gift. That was just the first door. In Section 4, let's step through door number 2, achieving the ultimate multi-sync. Now I want to pose a really critical hardware engineering question to you. Think about this. How do you synchronize multiple chips without them drifting completely out of step? Imagine you've got a master chip and several slave chips, and they all need to fire at the exact same fraction of a millisecond. If the timing drifts even slightly between them, your whole system breaks down. This is the classic master-slave synchronization dilemma. Well, here is the absolute gotcha moment that the creator realized. If you send the tick after the master chip has registered it, that signal has to travel across a physical wire to the slave chips, where it then gets registered again on their local clocks. That creates a two-stage drift. They're instantly out of step. The secret? You have to export the raw tick. You take the raw output straight from the comparator before the master even registers it. You send that single raw signal to every chip, including the master itself. Because they all receive the raw signals simultaneously, every single chip registers it on its own internal clock at the exact same boundary. No drift. So the crucial point here is captured perfectly by this really beautiful metaphor straight from the creator's build log: one heartbeat, many bodies. By exporting that raw tick directly from a free-running clock, you allow multiple separate PTSG cores across completely different chips to march in absolute flawless unison. But, to maintain that single heartbeat, you need some strict discipline. Here is the golden rule for slave chips. For this master-slave sync to actually hold, a slave chip must have absolutely no way to disturb the shared time base it's following. It cannot reset the prescaler from its own local program, it cannot reline it, and it cannot perturb it in any way. And this completely explains why the original design decision was made. Disallowing local programs from resetting the prescaler wasn't just about keeping the code tidy, it was a fundamental requirement imposed from the top down to allow this incredible multi-chip synchronization. The free-running clock is a shared resource and local programs simply cannot own it. Wrapping things up with Section 5. How exactly did we go from a liability to a source of capability? Let's extract the core design philosophy here. I want to read this directly from the source material because it hits the nail right on the head. A property you accept fully, instead of tolerating it, working around it, apologizing for it, can turn from a liability into a source of capability. This is so incredibly powerful. The creators spent the long time treating the free-running counter as this annoying constraint they had to manage. But the very second they stopped fighting it, the second they accepted it totally, without compromise, as a foundational principle, it stopped costing them and started paying massive dividends. It eliminated jitter, it gave them a cleaner hardware path, a higher top speed, and a flawless way to synchronize multiple chips. Trusting the clock to run free literally changed everything. Which brings us to our final slide and a provocative thought I want to leave you with today. Look at your own work right now. What liabilities or constraints in your current projects are you constantly apologizing for or trying to engineer your way around? What if you just stopped fighting them? What if they are just waiting to be fully accepted and transformed into your greatest capabilities? Sometimes the very limitation you're trying so hard to engineer away is actually the key to unlocking your project's true potential. Thank you so much for joining me on this explainer. I really hope this sparks some new ideas for you, and I'll catch you on the next one.